All right, good afternoon, everyone. It's a pleasure to have Professor Noson Yanofsky with us today. Professor Yanofsky is a professor of computer science and information sciences at Brooklyn College, New York, City University of New York. And unlike any typical computer scientist, he has a wide-ranging interest in mathematics, physics, computation, and even matters related to the mind. If you look at some of his works, you see the depth of these topics and the scope that he has gone into, not just in terms of the technical machinery, but also in terms of the analytic philosophy. He has written several books, but one of the most notable ones is The Outer Limits of Reason: What Science, Mathematics, and Logic Cannot Tell Us. And maybe he'll tell us a little bit about what's in that book. So it's a pleasure to have him here speak to us about today and tomorrow. Today's talk will be about philosophical matters, and tomorrow it will be the category theory connection. He has found a nice way to really connect the high-end machinery of category theory with physics, philosophy, and logic and computer science. So we are lucky to have him here. He came all the way from New York, driving 4 or 5 hours. He could have just sat on Zoom, but he wanted to meet all of you people. So it's a pleasure. Thank you.
Great. I saw from the camera. Oh, I'm supposed to talk here. Okay, so then we'll adjust our cameras. Hold on.
Adjust the camera.
It can be adjusted.
Oh, right. So this is a little bit brighter. Oh, okay. I think you're gonna want. I think you're gonna want to focus on one so that because we're gonna adjust this. Is that possible? Okay, so thank you for the introduction. My mother actually believes some of those things that he said about me. The gullible in that sense. She can make up some more of that. How do I go forward? How do I move forward?
This way is use this keyboard.
Perfect. Okay, so let me while they're talking, let me just tell you. So what this is I took 3 papers that I wrote. 2 of them I published, 1 of them I didn't publish. And down and up. Perfect. Okay, so they're basically on the same theme. Okay, they're on the same thing, but each one is a different aspect. And the theme is finding order within randomness, which is somewhat what's the word? Oxymoron. If there's order, there's no randomness. But I'm sorry. But first of all, let me just thank the organizers. Thank you for inviting me, and thank you for showing up. It'll be 2 hours, and then you can go eat supper. So let's just go through this. How do we find laws of physics? We discuss various philosophical issues. We show how laws can describe the order and structure within randomness. Okay, so that's the thing is I'm going to push this randomness thing. We also show how mathematics is related to these ideas. From this point of view, the last paper we talk about the unreasonable effectiveness of mathematics. Okay, so in a sense, what we're doing is as follows: 3 things. 1, showing that one can find order in randomness. 2, comparing that to mathematics, because you know what, we find a lot of structure in mathematics too, and we'd like to know how we do that. And the third thing is we're making an analogy because we find laws of physics, and we want to know why those laws of physics are expressed so wonderfully in the language of mathematics. Okay, so those are the 3 parts. Okay, so this is the basis of this talk. So one of these papers is called Finding Order in Chaos. There's a difference between randomness and chaos. I'm not sure what it is, but there is a difference. Okay, and I never published it, and you'll see why I didn't publish it in a minute. Okay, then we take a little literary detour through the Library of Babel, which is a short story by Jorge Luis Borges in 1941. I have a copy of it. I have like 10 copies of each of these. So if you grab, you get it. And please share with others. But everything is available on my webpage, and everything is available. The Library of Babel is available, and definitely should be read. It's 6 pages. It's something. Okay, we'll talk about that when we get there. Another thing is called finding structure in science and mathematics. And this was a winner. There were a few winners of a FQXI essay contest. FQXI is Fundamental Questions Institute. It's this amazing institute where people, Max Tegmark, whatever, people run, and they have amazing events, and they have these essay contests, and they do other absolutely amazing things at the edge of science. In other words, they're doing things that are out there and interesting, okay? Another paper I wrote, and this is about why mathematics works so well. So that's about the effectiveness, the unreasonable effectiveness, okay? And it's related to a work called The Role of Symmetry in Mathematics, which is I did with a friend of mine, Mark Seltzer. Again, all are available on our webpage, but I brought 10 copies here, and that would be nice. Okay, so first paper. The law is called Finding Order in Chaos. The laws of nature perfectly describe the universe in which we live. The goal of science is to find, describe, and characterize these laws. That's what physics is all about. Okay, as science progresses, we come to know more and more about our universe and its laws of nature. But what exactly are these laws? Why do physical objects follow them? Are they part of the universe, or are they metaphysical entities? I was told there are some philosophers here, so we're not going to talk about metaphysics, but we're going to talk about not talking about metaphysics. Why are they perfectly suited to bring about life, and in particular, intelligent life in our universe? Okay, so that's what we're going to do. Okay, scientists and philosophers have been agonizing over these questions for millennia. They've come up with many possible answers. Platonists and realists, I don't know what a realist is, except the Platonist, whatever. I don't know what I don't understand either of them. Believe in laws exist in a Platonic realm that is independent of humans. In other words, there's some attic that Plato described, and they live there perfectly, the laws of mathematics, the laws of physics, and I don't know how they communicate with each other, but they're perfectly done. Others have invoked a multiverse to explain the laws of nature. To them, every universe in the multiverse has its own laws of nature. The reason why we see such perfect laws in our universe is a mere fluke. The vast majority of universes within the multiverse lack useful laws of nature. Okay, and there's a few other things, but I'd like to push something else. Okay, there is, however, another way of viewing these laws of nature that we will explore. Rather than considering the universe to be totally ordered, consider all the phenomena in the universe and realize that they are not ordered, but mostly chaotic. When scientists look at the universe, they really act as a sieve, pulling out the order in the universe while discarding the majority of other chaotic events. Okay, I just want to say, I just drove 4 hours from New York City to here, right? And what did I do while driving? I looked at the beautiful clouds, okay? And there's a lot of strange shapes of clouds, okay? I couldn't find any patterns about them, okay? So what is it? It's not metaphysics, okay? So what is it? The shape of a cloud, but no scientist in the world is going to tell you about the shape of a cloud. They're going to tell you about the height of the cloud. We can determine different things. They're going to tell you about the color of the cloud. They're going to tell you about the thickness of the cloud, okay? But they're not going to tell you about the shape of the cloud. So that we pick and choose what we want to talk about. And we're going to talk about that. Okay, they concentrate on the order, ignoring the chaos. Okay, question. How do physicists pull out order? How physicists pull out order? Consider the classical problem of balls rolling down ramps. They have been a mainstay of physics since Galileo, okay? And Galileo had trouble with these things, and he had trouble getting funding for these experiments, and I'll explain to you exactly why. How long does it take for the balls to reach the bottom? Okay, I'm sorry, first-year students spend much time calculating every year aspect of the problem. Physics students sit there and they roll, and they do different experiments, and we'll talk about another one in a minute. How long does it take for the balls to reach the bottom? What is the velocity of the balls? Does the steepness of the ramp affect the acceleration of the balls? All these wonderful questions. While performing such experiments, the researchers must act like a sieve. A sieve is a colander, you know, where you mix spaghetti, okay? And ignore many aspects of those real-world experiments. So let's talk about some of the real-world aspects. The experimenter must ignore any friction of the balls on the ramp, despite the fact that that's physically impossible. You cannot roll a ball down a ramp without having friction. It's impossible. So you're talking about nonsense. Okay, the experimenter will not work. The experiment will not work if the balls are not perfectly spherical or the ramp is not straight. We must assume that the experiment is done at sea level, since gravity has different strengths at different heights. The experimenter cannot take into account what would happen if a person came in, stopped the balls from rolling down the ramp, even though that person is a physical thing. So we're ignoring that. So again, Sheldon's doing an experiment. He's rolling a ball down a ramp. In walks Kripke. He stops the ball from going down the ramp. You guys know what I'm talking about?
Yeah.
Okay. That's a physical process. Kripke coming in and disrupting is a physical process. So we can't do anything about that. Okay, so what we do is we ignore all those things and we say, assume it's frictionless, which is not, assume it's spherical, which is probably not, assume the ramp is straight, which is probably not. When Galileo was dropping balls, he ignored wind, air pressure. Okay, so he had them both, he had two balls of the same shape. So even though wind gets involved, he doesn't have to deal with that, or he tried to ignore that problem while he was doing it. Main point, only by ignoring all these cases and looking at the few keyword, idealized, this is what physicists do. They ignore things and they talk about the idealized case. Can physicists come up with the laws that describe the idealized balls rolling down the idealized ramps? Okay, physics does not study all phenomena, but rather the phenomenon that satisfies certain regularities. Randomness must be ignored. Physics does not predict physical phenomenon. It predicts predictable physical phenomenon. So you can't get more straightforward than that. But how do we choose which events are regular and predictable? How do we find the predictable within the random? With this in mind, we did the following experiment to find order within randomness. Okay, you'll see it in a second. It was done with a student of mine, Denise Mantes de Stoga. Anyways, we did this together. She wrote these amazing programs, and we did it. Ready? But here's randomness. Okay, it's a 35 by 35. This will be on the test. It's not memorized. Okay, we'll start 6, 4, 7, 6. Okay, you ready? This is a 35 by 35 array generated by random. Nothing there. Question, do you see any patterns in there?
Not quickly.
Not quickly. Notice 5, 5, 5.
6, 6, 6.
2, 2, 2. There should be there's a 6, 6, 6, 6. There's 4, 6.
Pattern.
It's just off the middle to the right.
Here, 6, 6, 6, 6, 4, 6. Okay, but there's other patterns too. For example, no, that didn't work. Well, but it's random. Okay, but you can search for patterns and you can find them. Okay, 9, 8, 7. These are just sequence patterns. Ready? 6, 7, 8, 4, 5, 6, 6, 7, 8, 0, 1, 2, 8, 7, 6, 6, 7, 8. Okay, it's there. Okay, hold on, there's more. These are solid things without changing numbers. 1, 1, 1. Here's those 4 6s I told you. 3 3s, 9 9s, 9 9s, 3 5s, 3 5s, diagonal. You can get a lot. Okay, it's an amazing. This was not published. It's too simplistic to publish, but it's there. It's amazing. I remember the first time I saw this. She made up this thing, and she showed me the results, and I was just blown away. I had sat there beforehand when she just showed me the thing, and I was looking for some of the patterns, and I found some, but I never in my wildest imagination thought that there would be so many. Okay, and sorry.
So how are each of these cells is independently random? You just draw uniformly for each cell.
Yes.
Wouldn't you expect this would be kind of the exact number of 666s that you
Absolutely. So let me just show you. So I did the math. Okay, and you do the math and you sit there and you count up what are the possibilities of finding a thing, and the math works out perfectly. So that's another reason why I didn't publish. I didn't get anything different than what math predicted, but it's still amazing the amount that math predicts. And again, I just did a 35 by 35. If you did a lot bigger, you'd probably find more interesting. And you could start searching for other things than just number, or number plus one, number plus two. So they are filters. They show the extracted order that can be found in chaos. The numbers do not contribute to the order, The numbers that do not contribute to the order are left out. So I left the rest blank, so you can see it. This is exactly what scientists do when they look for laws of nature. They let all the unstructured parts fall through their fingers. The shape of the cloud falls through their fingers. They're not interested in that. Of course they are interested in that. They just don't have any formulas for it. Okay. Okay. They let all the unstructured part fall through their fingers and concentrate on the ordered parts. Okay. Now open up your newspaper. Boys and girls, there used to be something called a newspaper, okay? And they have the funny pages, which is the only part worthy of reading. Next to the funny pages, they have the puzzles. Anyways, what you have is word find, right? You're given this array of letters and you have to find, they show you which words to find and you have to find them. The popular word search puzzle found in the fun pages of the newspaper is also about finding certain patterns. There's a matrix of letters and you have to find the words. There is, however, one major difference between word search and our experiment. The makers of word search puzzles put the hidden words in. I didn't put the hidden words in. I randomly chose them. That's a very strange thing. I mean, whatever, that's the major difference. In contrast, we did not put in any patterns in our matrix. Random numbers were entered and yet patterns exist. Go.
Isn't it just half of what scientists do? Because the other half is, okay, take a pattern, generalize it, and see if it can be falsified based on the data.
Perfect, exactly. And we talk about that. We're going to do that. Okay, sequential. So this is, we can find other patterns too. Sequential patterns are not the only patterns in the chaos. There are many other types of patterns. For example, why not look for not x plus 1 and x plus 2, but x plus 2 and x plus 4, or different longer sequences. Look for the digits of pi, look for Fibonacci's numbers, or look for, why look for straight lines of things, look for squares and squares and three blocks of things. Okay, a suggested project. Okay, so this is a school, they have projects, you have to present your project. So here's a nice project. Okay, I thought about it, I have some ideas of, well, but it's a nice little computer project. Extend this experiment, add a time dimension. Okay, so instead of looking at a two-dimensional array, add a third dimension, which corresponds to time. So this is what all totally randomness, but this is what it looks like, this is what it looks like next, this is what it looks like next, et cetera, and see if you have any patterns going through time. In fact, you'll probably find more. And the reason is very simple. First of all, a three-dimensional array has, let's say you're doing a 35 by 35. So you're going to have a 35 by 35 by 35. You're going to have 35 times more numbers than before. And also there's more directions that you can look. Okay, think about it. When you have a 3 by 3, so you can go this way, this way, this way, this way. You can basically go 4 directions. But when you have a 3 by 3 by 3, you can have all different types of directions that your numbers can go into. Anyways, and I have some ideas about this. I just, whatever. For example, the more you search, and that has to be quantified complexity theory-wise, the more you'll find. Okay, how complicated are your patterns that you're looking for? Okay, and also some type of Noether theorem about preserving things as time goes on. So Noether is very much into this type of symmetry and stuff like that. So that's an interesting project. If you do it, send me an email. Include me as a co-author, whatever you want. But I have some more ideas if you want to talk about it. Okay.
I have a quick comment and a quick question, if that's okay. If you go back a
No,
slide.
good criticism. I like criticism. Go.
you said looking at digits of pi. I was actually thinking about this on your last slide with the 35 by 35 grid. There's a movie called Pi by Darren Aronofsky. It's an amazing movie, and it's about a mathematician who's obsessed with trying to find patterns in the number pi. And it's a crazy movie. Like it starts with a simple premise, and then there's lots of.
I grew up on a street in Brooklyn called Avenue J and East 17th Street. On the corner of J and East 17th Street, there's a school, and Darren Aronofsky went to that school.
It's a really great movie. Anyone?
That's a pattern.
That's a pattern. Anyways, with a wonderful ending. Should I give away the ending? No.
No. The ending's great. Don't give away the ending. Then the quick question, if I may, I mean, with the example of the clouds, you say, you know, a mathematician can't describe the shape of the cloud. To what extent is it we can't describe it yet because we haven't looked hard enough? And to what extent is it can't be done? Because I could envisage someone could do a massive data project where you get millions and millions of photographs of clouds, and you could maybe make a probability distribution of the shape of clouds. And it's not super deterministic, but you know, there's some prediction that can be made.
Fractal dimension.
Hmm?
Fractal dimension of a cloud.
Yeah. Congratulations, you've now invented statistical mechanics.
Right. Thank you.
Well, you know, Boltzmann and Gibbs had their chance, but obviously, right, so there is something, I mean, Boltzmann and Gibbs would say something about that.
Yeah.
No one's gonna give you an exact formula for it. Not that it's physically impossible or logically impossible, it's computationally impossible. Namely, it's beyond NP complete, et cetera, et cetera. And you have to come to tomorrow's talk to understand that.
Okay.
Okay, so let's talk about, oh, sorry, go.
Can I ask a quick question?
It's
It may be a dumb question, but it seems that there are a lot of kinds of patterns that you can draw from that examples. Like it's a sequence, like it's a pi. So it seems to me that it all comes down to what you define as patterns. So wouldn't it be like to getting the example of clouds, for example, when we are kids, we look at clouds and if you look long enough, oh, it seems like a duck, it seems like a horse. Wouldn't it be like this in a philosophical way? Like if you look long enough, you always find patterns, but different person find different patterns and so on.
right, so I'll answer that two ways. One is technically, so I had some type of theorem about the longer you spend looking for patterns. Okay, so it's, you know, the longer, the larger that computer program is, the more patterns you will find. So that's a technical result that you'll get. So, okay, you'll look it up later. There's something called the interesting number paradox. No, never mind. Anyways, but the point is, yes, you can get more, but that's my main, the philosophical point is my main point, namely, yes, we're always looking and we're finding patterns and we're saying there's structure there, but it's more interesting than that.
I see. Thank you.
Okay, so let's talk about the Library of Babel. It's a short story. It's over here. You can take it, whatever. So let me just describe it. Short story presents a universe conceived of an infinite library containing every possible book of uniform format, filled with every conceivable combination of letters and punctuations. So it's the story takes place in a library and it's narrated by a monk or a librarian. And there's hundreds, I'm sorry, there's a question of there's infinite or not. There's not an infinite number of rooms, and there's not, but every single book is 410 pages. Every single book has 40 lines on the page. I think there's 26 characters, and they have every single possible book, including all the answers to life's great mysteries, including every Douglas Adams book, et cetera, excluding all the scripts to the Big Bang Theory, whatever, they're all in there, okay? But you can't find it, okay? So he's describing what this thing is, what this library is and what it has. I'll explain to you why it's important. This includes not only all works ever written, but also endless variations, nonsensical texts, okay, and even the catalog of catalogs. The inhabitants, known as librarians, dedicate their lives to the futile search for meaning amidst the vastness. While the library theoretically holds all knowledge, the sheer scale of the meaningless and unintelligible text renders any meaningful search virtually impossible, driving many to madness, suicide, or cultish pursuits of illusory order. So he describes that there was some librarians who got together and they decided to throw out all the meaningless books, and that way we'll have only the good books. But how do you determine if it's a meaningless book or not? Let's say you find a book that makes predictions about what's going to happen next year. How do you know if that book is a good predictions or bad predictions? Okay, and so they stop the people from throwing out books. But again, and you know, there's like legends among these librarians that somebody once found a book that had all this or had all that. Again, it's 6 pages, it's worth reading. The story profoundly emphasizes humanity's inability to gain total knowledge, despite its theoretical availability. Again, the answer to life's great mysteries are in that library. Okay, but no one can find it. Okay, the librarian possesses the potential for universal understanding within their grasp. Yet the overwhelming quantity or irrelevant or nonsensical information acts as an insurmountable barrier. It's not going to let you find it. True knowledge becomes indistinguishable from chaos, and any discovery of a coherent text is a statistical anomaly in the sea of gibberish. This highlights the paradox that boundless information can be as debilitating as utter ignorance, demonstrating that the sheer volume of data without method for discernment, telling what's good and what's not, leads not to enlightenment, but to despair and the recognition of an inherent limitation of human comprehension in the face of true infinity. Now, let's get back and apply this to our things. Only by idealizing and limiting what we are looking for can we make progress in science. The librarians in Babel did not do that, so there was no progress. In other words, they had this cult that was throwing out old things, and they were throwing out random text. And there was a valid criticism against them, namely that you don't know what's a valid text and what's not a valid text. But when we deal with science, we do throw out nonsense, or we do throw out things we can't control or comprehend. Okay, now I'm not saying this. This now it comes a quote from authority. So, you know, like you can't argue with me. This is Eugene Wigner, okay? And this is not just in one of his papers. This is his Nobel Prize accepting speech. Okay, so he knew everyone's going to read this speech, and listen to what it says. It is clear that in this sense, physics does not endeavor to explain nature. In fact, the great success of physics is due to a restriction of its objectives. It only endeavors to explain the regularities in the behavior of objects, predictable behavior. That's what he's talking about. He doesn't want all behavior. You can't get all behavior. Okay? This renunciation of the broader aim and the specification of the domain for which an explanation can be sought now appears to us an obvious necessity, period. Now the next sentence. This is a boom. This is kaboom. In fact, the specification, in other words, saying, oh, we're just dealing with that, of the explainable may have been the greatest discovery in physics so far. Not me saying it, Eugene Wigner. That's an amazing statement. He's saying, look, what we have to do is not find regularities, is ignore some of the things. That's what we're doing. It's an amazing statement. Okay, so.
Can I ask you, I mean, isn't it true that like, that's also the low-hanging fruit, like the explainable is?
Right.
I mean, is it really a great discovery that you figured out all the easy things?
No, the point is, we can only figure out the easy things. That's the.
He's saying, it seems like he's saying that the greatest discovery. So why is that the greatest discovery?
I'm just trying to discover the mouse where the stupid arrow. Why is that? Because we wouldn't have made progress in physics without it.
I feel like you're kind of chasing your tail when you say that, though, you know?
Criticizing me or him?
I guess I'm criticizing the interpretation.
Okay.
Yeah.
So how would you interpret it?
Well, that's what I'm saying. I don't know how to interpret it otherwise, is the thing.
Anyways, it's a page and a half. It's worth looking. Go, please.
I would like to add to a comment that was made earlier regarding, with respect to the digits of pi, which you mentioned in one of the earlier slides. some people think the digits of pi behave randomly. If we find the digits of pi somewhere, do we should we say we found randomness or we found order?
Did you ever read the book Contact by Carl Sagan?
I heard of it.
You should read it because he shows you that the digits of pi are not random. By the way, the digits of pi are not random anyways. I can write a program that doesn't. So they're not random at all, in any sense of the word.
But yeah, the pseudo randomness in a certain sense.
I mean, it's a normal number, right? Like all the numbers appear with equal frequency, right? Yeah.
Probably, right,
So they think.
right. But it's hard to define random.
Yeah.
Okay, the talk is over because I can't move forward because I lost, oh, there it is. Good. Second paper. Okay, so that's the first. Again, I never published this paper because I don't know what to do with it. It's shocking and yet it's obvious. He pointed it out right away. It's obvious, you know, that I actually do the math and I show that the amount of things sort was found. Anyways, okay, finding structure in science and mathematics. We're moving a little bit slow, so we're going to do this a little bit quickly. One can view the laws of nature as having goals and intentions to produce the complex structures that we see. But there is another deeper way of looking at our world. The universe is full of many chaotic phenomena. There's going to be a little overlap because it's the same thing, but we go a little further with this. The universe is full of many chaotic phenomena devoid of any goals and intents. The structure that we see comes from the amazing ability that science have to act like a sieve and isolate those phenomena that have certain regularities. By examining such phenomena, scientists formulate laws of nature. There is an analogous situation in mathematics in which researchers choose a subset of structures that satisfy certain axioms. In this paper, we examine, so this is not just about science, this is about math and science, and you'll see the way they work together. In this paper, we examine the laws these two processes, we examine the way these two processes work in tandem and show how science and mathematics progress in this way. The paper ends with a speculative note on what might be the logical conclusion of these ideas. Okay, again, we have to talk about laws of nature, how wonderful they are, and they do things, and they're expressed in mathematical logic, language, and what reasons are there, Platonism or realism. The multiverse, okay, but we're not interested in talking about that. There's another more interesting explanation for the structure that is the focus of this paper. Rather than saying the universe is very structured, say that the universe is chaotic and lacks structure. The reason why we see so much structure is a scientist acts like a, okay, we select the phenomenon. You've seen this before. I just wanted to say it because now we're going to talk about another way of finding the order. Okay, so we talked about finding it using these computer programs, but I'd like to take the real, so that's about finding structure in numbers, in an array of numbers. But now I'd like to really talk about what physicists do, and what they do is, it's called symmetry. Okay, things that, so what does physics do? Not predictable, but things that have symmetry. Okay, symmetry is the property that despite something changing, there is some part of it that still remains the same. When you say that a face has symmetry, you mean that if the left side is swapped with the right side, okay, it will still look the same. When physicists use the word symmetry, they are discussing collections of physical phenomena. We're going to get into this much deeper in the third paper. A set of phenomena has symmetry if it's the same for after some change. The most obvious example of symmetry is location. That means if you do the experiment here, or you do the experiment in New York City, you're going to get the same results. You have symmetry of time. If you do the experiment today, or you do the experiment tomorrow, you get the same results. Okay, and orientation, there are many other types of symmetry. We'll get into that with the third paper. But I want to talk about we're going to talk about this. This is like that thing about the ramp with the balls. This is just another example. If phenomena is to be selected by a scientist, then they must have some different types of symmetry. They must have some different they must have many different types of symmetry. When a physicist sees a lot of phenomenon, she must first determine if this phenomenon has symmetry. She performs experiments in different places and at different times. If she achieves the same result, she then studies them to find the underlying cause. In contrast, if it fails to be symmetric, she ignores it. Okay, and this is a big political thing about reproducing papers in biology. You know, whether reproducing experiments in biology. So this shows up now. There's actually something deeper going on here. The laws of physics cannot be found without bracketing out. That means pulling out phenomena. Consider the way the laws of physics are given, and they taught in physics class. Okay, so this is like the balls rolling down. Ponder the simple law that Newton taught us about gravity. The force between two objects, F is equal to m1 times m2 divided by distance. The force between them is given by the product of two masses divided by the square. This is only useful when the two bodies are spherically symmetric. Okay, so the pin, what is it? The midpoint, whatever, it has to be spherically symmetric. The bodies also have to be totally homogeneous. Same, the mass has to be the same all over. There cannot be a third body or gravitational force affecting either of the bodies. Okay, both bodies must be magnetically and electronically neutral. They cannot be traveling at the speed of light, otherwise you have to talk about special relativity. The bodies also cannot be too small, lest quantum effects come into play. I love doing this. Ready? Here's one body, my keys. There's another body, planet Earth. Okay, and we drop it. But it ignored something. What did it ignore?
Air resistance.
Huh? Well, air resistance, that's one thing. What else did it ignore? It ignored my weight, which is a very, I like that it ignored my weight. It's actually a three-body problem here. And as far as we know, oh, I'm sorry, I didn't do this in the camera. As far as we know, okay, my weight problem never affected the trajectory of these keys going down to its planet Earth. That's no. If gravity can ignore it, why can't I die? Okay. In summation, it's safe to say that there's probably never two bodies that exactly satisfy the requirements of Newton's law to be exactly true. Again, we idealize. Not we, Newton idealized. Go.
I just didn't understand the connection between symmetry and the bracketing out. Could you repeat that?
We bracket out by searching for symmetry. Those that do not, in other words, we ignore all things that don't have symmetry in it. So for example, I drop my keys here. This is my other keys. We drop my key here, and if I got a different result, if I drop my key there, then you would say, oh, that's not part of science. So we ignore the rest. We idealize the rest. We say, oh, Yanofsky's weight problem doesn't affect gravity.
So which type of symmetry was that right now?
That's called symmetry of locality. Okay, I do the experiment in different places. And if it doesn't satisfy symmetry of locality, we don't keep it in. We bracket out all things that don't have symmetry of locality. Go.
I understand what you mean when you say that, for example, when you drop your keys, like the mass associated with your keys ignores your body weight because planet Earth is so bigger. But maybe this is connected with something you said about, oh, we idealize the word, so we forget about friction. But maybe my understanding is that indeed your mass has an effect on the key, but it's so negligible that if we idealize it, it still works. So I think it's a little bit different from saying that, oh, it does not affect, my body weight does not affect the key or something like this. So what do you think about that?
Okay, so let's be clear. It does affect. And it is a three-body problem. Yes, it's negligible, and us humans ignore it, but it does affect. Main point, the rule F is equal to m1 m2 divided by d squared is not true. Okay, we don't, because there is and I'm sorry, it's not true. It's not true in the case of the keys and the Earth.
But presumably it doesn't purport to be true in the case of the keys, the Earth, and you, right?
Right. We don't have a solution to the three-body problem.
Oh, okay.
We
Three-body.
like we don't have a closed form nice solution to it, but like we use that same rule and we apply it amongst another theoretical framework and we come
Right,
to
so,
more accurate.
so we idealize, so what does Newton's rule apply to?
An idealized form where you have two bodies.
Right.
But it does generalize, right? Like it's not like we need a different version of Newton's rule when we have three bodies and we're putting it into, so we compute using Newton's law when we have three bodies. We just do a bunch of computations, right? We compute the force between each of the pairwise objects.
No.
Well, that is how we would do it, right? We would take a lot of computational steps, but
Wouldn't work
that's.
at all, it would be an infinite process. Wouldn't work at all. I'll prove it to you. Ready? What is the length of a lunar year, of a solar year?
8
Come on, without looking at Google, you know that. What is the length of a solar year?
365 days.
And
And a quarter.
Sometimes one
a
extra.
almost a quarter, a little less than a quarter. Okay, good, great. Now let me ask you another question. What is the length of a solar month? Time that the sun I'm sorry, the lunar month, the time that the moon goes around the earth. Okay, you can look in Google.
30 days.
About 20 days, 28 days.
Look what Google says. It's very interesting. Type in solar month. I'm sorry, lunar month.
But it's the point that it gets affected by the sun, right? So of course, like you can't use one body and second body to compute if there's a third body, but
Right.
you can use the force, the pairwise force
It
between
doesn't
them.
say that. Read the sentence.
The length of the lunar month,
It varies.
the average length.
The average length of the lunar month is 29.5 days. What does that mean? Doesn't say the average. Look at the solar year. Doesn't say the average month. In fact, it's usually not 29.5, and it can vary up to 15. It can vary up to 15 hours. If you celebrate Ramadan, okay, you do not know when Ramadan is beforehand. Open your calendar. It doesn't say when is Ramadan because they don't know when it is. Okay, and the reason is because the lunar month varies. Okay, and it's because of the three-body problem. I don't know of a way of solving the three-body problem using a lot of two-body problems.
Yeah, let me be
You
more
could
specific.
simulate a lot.
That's exactly what I mean, is that
Right.
you can simulate it, and to simulate it, you need Newton's law or a more generalized version using, you know.
But I don't think your simulation will be very successful.
It has to be, right? We launch rockets and they get to where we want them to go.
We make idealized statements about the logic, the thing. I mean, where do you see the three-body problem in the rocket?
I see a many body problem. You have the rocket's traveling, there's a bunch of different gravitational bodies. The rocket ends up, doing a loop around one, getting to the other, and you pull from this is how physicists did things a long time ago and they still do them now, right?
Well, I think what you're saying is that it's not the three-bodiness or the multi-bodiness that breaks Newton. It's really like quantum stuff, like it's a classical law, right? So it's a non-relativistic, non-quantum law. That's where it breaks. Like Newton's law is fine as far as you're away from these scales, right? It doesn't, the number of bodies, the law is the law, as long, you know what I'm saying? Like as long as you're not in a quantum setting or a non-relativistic setting, there's no reason to suspect that Newton's law.
For two objects, but he's talking about what about for three objects?
It works for more than two objects. It just doesn't work as simply as give me two numbers, I'll multiply them, divide by the radius. Like I use this and I put it into a bigger framework. That framework, if I didn't have that law, I would never be able to come up with a simulation for how three bodies are moving around. I need that law. That law is not sufficient, but it is necessary.
But we have to talk about how effective or how good your simulation is.
It can be arbitrarily effective, right?
Okay,
Sorry,
I'm not starting over Newton.
Sure.
Whatever, the rule works and it's an idealized rule. We just have to realize, we have to accept the fact that it's an idealized rule. And for the most part, it really doesn't make a difference. Right, I mean, it's minor. If things are, but in large cases where the moon is being affected by both the earth and the sun, it does make a difference. And by the way, I do not think that there's a formula to tell you when the new moon is next moon. I don't think there is such. I don't see it anywhere. type in, when is the next time?
No,
you see
I
it?
agree, yeah, I'm not.
Oh, just a quick comment to just what I'm taking away from the general concept is we can only account for the stuff we can account for.
Or physics only predicts predictable phenomena.
There we go.
So are you saying that the simulation that he's referring to would at best be an approximation?
I think so.
Yeah, but it's not a problem with the law. It's a problem with like the time scale of simulating. That's a different problem, is the distinction that I think we need to be clear about. Like, as far as we can tell, the law is fine, right? It's a question of simulating the law, right? But that's a different thing. And maybe that's what you want to say.
The two-body problem law is perfect.
It's not. It's also an approximation. It's a non-relativistic, non-quantum approximation.
Okay, so with that idealization, we're talking about this the two-body problem and the three-body. Let's not go. Anyways, he wants me to finish by 5 o'clock.
I'm sorry, yeah.
No, it's okay if you do, just a little more time, it's fine. No.
See that I can use that as an excuse. Summation, it's safe to say that there are probably never two bodies. Rather, the physicists must make controlled experiments and ignore all these other effects. By selecting the phenomenon, he realizes it. Without selecting the phenomena, no such law can be found. Okay, now that's physics. I want to talk about numbers. Okay, and I want to talk about problems. The idea that we only see structure because we are focusing on a subset of phenomenon is novel and hard to wrap one's head around. We think that here's the way normal people think about physics. There's structure in the universe. Physicists come around and they find that structure and they find those laws, and that's very nice, and they get paid. Okay. This is a little bit different. This is saying there's a lot of phenomenon. We find what there is, we ignore the rest. Okay. There's an analogous situation in mathematics that is much easier to understand. We will focus on one of the important examples where on this selection process is seen very clearly. It's somewhat easier to see in the math, and you'll see why in a second. First of all, because math is idealized anyways, so we don't have to worry about it. We will focus on that. First, we need to take a little tour of several number systems and their properties. Consider the real numbers, which are totally ordered. What does it mean, totally ordered? I give you one real number, I give you another real number. Either one is less than the other, or the other is less than that, or they're equal. Okay, so that's totally ordered. While the real numbers seem like a complete picture, the story does not end there. Although already in the 16th century, mathematicians started looking at complex numbers. You know what a complex number is. Since a complex number is built from two real numbers, we usually draw them in a two-dimensional plane. The real number sits on the complex plane. The reals are one line, you have the whole plane. Okay? We do this in 10th grade nowadays. Okay. This corresponds to the fact that every real number R1 can be seen as a complex number R1 plus R plus 0i. So the real numbers have 0i. Very good. In contrast to the real numbers, the complex numbers are not totally ordered. This has to be clarified if you want to argue with me, and I can do that, but I don't have to do that. And given two complex numbers, 3 plus 7.2i and 6 minus 4i, can we tell which one is more and which one is less? Okay, now you could talk about the modulus, you could talk about the distance from the circle, from the thing, but that's not totally ordered. Okay, because everything on a circle around would be the same order, would be the same distance. But there's no way, okay, so let me give you the details. There's no way to order the plane that respects the multiplication. Okay, the fact that the complex numbers are not totally ordered means that we lose structure when we go from the real numbers to the complex numbers. Okay, great. So keep this in mind, real and complex. Next, the story is not over with complex numbers. Just as we can construct the complex numbers from pairs of real numbers, so too one constructs the quaternions from pairs of complex numbers. Here's one complex number, here's another complex number, and we can use that to get quaternions. Quaternions are have four things in them, okay? And if you ignore the last two of them, make that 0, 0j and 0k, then you're going to have complex numbers. So the right way to think of it is you have the real numbers sitting inside the complex numbers, which sit inside the quaternions. Okay, now let's keep this in mind. Quaternions also lose structure. okay? And they have even less structure than the complex numbers, while the multiplication of complex numbers is commutative. C1 times C2 is equal to C2 times C1, okay? It's not true for quaternions. In general, it's not true for when you multiply them, there's a way of multiplying it. When you multiply them, you don't necessarily get commutative. Okay, great. This process of doubling a number system is called the Cayley-Dixon construction. It's a very nice thing. It's not used enough because whatever, but it's a very nice way of doing things. And you show how do you do this. So guess what we can do? We can take the quaternions and go to the octonions. Okay, we get octonions. Octonions are made out of 8 numbers, okay? But they also lose structure and they fail to be associative. So when you multiply them, they're not associative. A times B times C is not equal to A times B times C. There are 2 ways of associating things, need not be. Okay, there's no reason to stop at 8. You can go on to 16. They're called Sedinonians, and there's even a 64. Each one loses some structure. Okay, the main reason why people stop at octonians and don't go to Sidonians is because there's no way to divide Sidonians. Okay, with real numbers, I can add, multiply, subtract, divide. Same thing with octonians. I can add, multiply, subtract, and divide. With Sidonians and higher, you can't divide. And physicists have a hard time using this, and mathematicians have a hard time dealing with it, and it's just not great. Okay, let's talk about applications of these things. Let's keep in mind where we have real, complex, quaternions, octonians. Just stop there. We don't have to talk about the science fiction. And those things don't really exist. Like the number 3 really exists. Okay, -3 kind of exists. Minus square root of 3 doesn't exist. No, I'm just kidding. I'm just trying to make the philosophers happy. Platonists have everything very neatly on their shelf somewhere in Plato's attic. Good. So here's a picture of what we have: real, complex, quaternions, octonians, Sidonians. Forget about those. Main point: this is ordered. The complex numbers is commutative. Anything above that is not. The quaternions are associative. Anything above that is not. The octonians are division. You can divide 2 octonians. There's a way of dividing 2 octonians. Anything above that is not. So while you're getting higher and higher, you lose information. You lose structure. Okay. Okay. This is interesting for physicists. We're going to ignore them for a minute. How are these things used? Well, the real numbers are always used. Complex numbers are used in wave mechanics, they're used in quantum mechanics. Some people do some type of interesting stuff with quaternions, but not really. The rest are barely ever used in the real world. Okay, but let's forget about applications. Let's just talk about that. The usual view of these number systems is to think that the real numbers are fundamental, while the complex quaternions and octonians are large, strange, larger sets that keep mathematicians and some physicists busy. The larger number systems seem unimportant and less interesting. Let us turn this view on its head. Okay, so this is the main point of this paper. Rather than looking at the real numbers as central and the octonians as strange larger number systems, think of the octonians as fundamental and all the other number systems as just special subsets of octonians. So that's the important thing, the octonians. The only number system that really exists is the octonians. To paraphrase Kronecker said something about the integers, but let's use him for something else. Again, proof by authority, but this I made up. Okay, God made the octonians. All the rest is the work of man. Okay, that's not true. I said it, but we can attribute it to Kronecker. People.
He said integers or
he said natural numbers. Okay, we do the same trick with the Sidonians and even the 64 dimension systems. Let's just fix the ideas with the octonians. Let's go further. Okay, great. Let us explore how we can derive all the properties of number systems that we are familiar with. Although multiplication in octonians is not associative, If you want an associative multiplication, so again, actonians fail associativity, but if you want, what you can do is you can look at multiplication not of all actonians, but the only special types where these are all zero. What do we call that? Quaternions. Okay, and if you want, if one further looks at all the actonians of the form like that, in other words, all the last 6 numbers are zero, then the multiplication will be commutative. So look what I'm doing. I'm looking at subsets of actonians, and I'm finding more and more structure when I look at subsets. That's an amazing thing. Okay, complex numbers. I can have 7 of the 8 actonians, and again, there is a nice theorem of how, I'm sorry, there is a nice definition of how you multiply actonians. And if you use that definition, but only with special things like this, then you get a totally ordered system. All the axioms that one wants satisfied are found sitting inside the actonians. So again, actonians have very little structure, but if you look, examine little subsets of it, you find structure. Right. What does this have to do with physics? Okay, I'm sorry, this happens all the time. You have a group. If you look at those elements, x times y is equal to y times x, then you just ignore the rest of the group. So every group has inside of it an abelian group, commutative group. Okay. Let's look at that. Great. Okay, great. So we have physics, and what do we see? We bracket out information. We look at subsets of information, and we get structure. We have mathematics, okay? We bracket out information. Sorry, we look at subsets of mathematical structures and we find more structure. Same process both ways, okay? Good. So you're all physicists, or you want to be physicists. The job of physicists is to describe a function from the collection of observed physical phenomenon to mathematical structure. So this is what you want to do the rest of your life. Think about it. You really want to do this. Could be a truck driver. And whatever. Observe physical phenomena, and you want mathematical structure of that. Okay, that's what you do. You see something and you make. If you write a physics paper and you don't have math in it, it's not going to be published. It's just, well, I really think that it's just not going to be published. It doesn't work like that. So what you have to do is you take physical phenomenon and you have to make of it mathematical structure. That is, we have to give mathematical structure to the world we observe. By the way, that's an interesting question. Why do we have to do that? Why is it that publishers won't publish a paper without math in it? We'll see that in the third paper. We have to give mathematical structure to the world we observe. As physics advances and we try to understand more and more observed physical phenomenon, we need larger and larger classes of mathematics. In terms of this function, if we were to enlarge the input of the function, we need to enlarge the output. Let me explain. You have some physical phenomena. You have some structure that corresponds to it. Now you observe a new physical phenomenon. So you're going to make this bigger. You're going to be able to observe more. You're going to get, you need larger math to get it. You need more math. Go.
Okay, so this feels very inductivist, right? We observe more of the world. As we observe more of the world, we come up with the underlying structure of the world.
Right.
But it feels like, in fact, the way that we go about making observations in the world is we first theorize about them, we try and come up with some hypothesis, and then we have to look somewhere specifically. We have to look deep in order to find out whether or not our structure is true. So it's not so much that we observe physical phenomena and come up with a mathematical structure, it's that we come up with the structure and we go look out into the physical world to see if we falsify it.
It's a back and forth, isn't it?
Could we come up with this 2 slides from now? Because I give 5 examples.
You shut me up whenever you want.
Okay. But no, seriously, this is, 1 second. Let's just make sure the camera's working. This way. First of all, there's a podcast I just watched, or an interview with Terence Tao. Terence Tao is a great mathematician, and he was just a 3-hour interview with Lex Friedman. Okay, and it's fascinating. Every 10, whatever, Lex Friedman chopped it up into 20 different things, whatever, but it's absolutely fascinating. And he says a very interesting thing in there. He says one of the hardships of getting a unified theory of everything is that we have already a nice theory of quantum physics. We have already a nice theory of general relativity, and they work for 99.999% of physical phenomenon that we observe. The only place where they don't work is the Big Bang or the black holes or very small places or things like that. I don't want to, he's not, how he quantifies 99.99% is not important, but the point is, it's a very, so he says it's hard to come up with a new thing where we don't have so much experience with those things. Okay, we don't have the answer to the, what is that called, the information paradox of black holes, because we don't know. So how can you make predictions? So again, what he's doing is we have for the input of quantum physics, we have a mathematical structure. For the input of general relativity, we have a mathematical structure, but we don't have something for the union of those two. Okay, just give me a second. Okay, so some examples of this broad, oh, sorry, let me just go. That is, we have to give mathematical to the world we observe as physics, as physics advances, and we try to understand more and more of these physical phenomena. By the way, what he said, Terence Tao, if you think about it, think about Einstein. He never had access to something going close to the speed of light. And yet he formulated special relativity or general relativity like that. It's a very interesting thing, even though he didn't have access. And I mean, we all have access. I mean, the speed of light is going right now, but he didn't know these things, whatever. General relativity wasn't proven, quote unquote, until a few years after it did. In terms of this function, if we are to enlarge the input of the function, we need to enlarge the output. By the way, Einstein didn't get the Nobel Prize for special relativity or anything like that. He's holding his mouth. Okay, I told you I can get him to be quiet. No, just kidding. Okay, some examples of this. Let's do some examples of this. I have 5 examples, and you can think of a million other examples. I had 5 examples when I was writing this, but let's do this. When physicists started working with quantum mechanics, they realized that the totally ordered real numbers are too restrictive for their needs. They required a number system with fewer axioms. They found the complex numbers. Okay, why does the physical world need complex numbers? Interference, and you have interference not with complex numbers. You don't have it with real numbers. Okay, don't want to answer any questions on that one. Okay. When Albert Einstein wanted to describe general relativity, he realized that the mathematical structure of Euclidean space and its axiom of flatness, it's called Euclid's 5th axiom, was too restrictive. He needed curved, non-Euclidean space to describe the space-time of general relativity. And there's some type of quote, I've seen it, but I can't find it, and I couldn't find it. There's some type of quote, there's some type of story that Einstein figured out special relativity in 1905, and he didn't come up to general relativity until 1914. At some point, he was struggling with it, and his friend Grossman, or his friend this one, whatever, showed him a book on non-Euclidean geometry, and he was blown away. Some people say it was a Riemannian geometry, but the main point is he didn't want to deal with the flat geometry, Euclidean geometry that he knew from high school. He needed this curved geometry. And the way to think of flat geometry is as a subset of all geometry. In other words, you have axioms, non-Euclidean geometry, you have axioms of non-Euclidean geometry, and one of them that you don't have, an axiom that you don't have in non-Euclidean geometry, is this called Euclid's 5th axiom, the parallel axiom. And it goes as follows. How does it go? It goes, if you have a straight line and a point, okay, this is Euclid's 5th axiom. If you have a straight line and a point, then you can draw another line that's parallel to it. you can draw exactly one other line that's parallel. Okay, that's called Euclid's fifth axiom. It has a fascinating history. All of Euclid's other, do you know this stuff? Okay, so we'll leave it. Hold on one second. For more about this amazing topic, you too should read The Reason, What Science, Mathematics, and Logic Can Have. MIT Press. So the main point is Euclidean geometry is a subset of non-Euclidean geometry. And he wants to go from special relativity to general relativity. He has to go from the subset of flat space-time to curved space-time. And supposedly he had said that he found it very spooky that what he needed was done decades earlier by mathematicians. Okay. Third example, in quantum mechanics, it is known for some systems, if we measure X and then Y, we will get different results than first measuring Y and then measuring X. In order to describe this situation, mathematically, one needs to leave the nice world of commutativity. They require the larger class of structures where commutativity is not assumed. Okay, so X times Y is not equal to Y times X. Now that's a strange thing. It's another thing that was done earlier. The mathematicians did that earlier than the physicists, okay? And Heisenberg had come to his teacher and showed him, look, he has this great way of describing quantum physics. And his teacher, Jacquard, I think, or something, said to him, congratulations, you discovered matrix multiplication. Okay, which was done earlier. Hold on, more. Boltzmann and Gibbs started talking about statistical mechanics. They realized that the laws that they were coming up with were no longer deterministic. Outcomes of experiment no longer either P of X happens or does not happen. That's deterministic. This happens or this does not happen. Okay. Rather, with statistical mechanics, one needs probability theory. The chances of a certain outcome of an experiment is probability. P of X is an element of the infinite set between 0 and 1. Rather than the restrictive finite set just having 0 and 1. So this is the interval of real numbers between 0 and 1. This is 0 and 1. Okay. When scientists started talking about logic of quantum events, okay, this is a little bit thing. This is about quantum logic. We don't have to get into it, but you can think of 10 more. If with the history of physics, you can think of 10 more examples of this stuff where you need more advanced math. Now, can you ask your question?
I have a couple. It might be worth waiting until you vote.
Okay, good. No. I don't have to answer that later, right? Many other examples exist. Okay, again, I need a quote from authority. Okay, so this is Paul Dirac. Okay, this is from the 1930s. Can I just strongly recommend, if you're going to be a physicist, whenever you have a chance, read Paul Dirac. Okay, read his. Don't read Griffith's quantum mechanics. Read Paul Dirac's quantum mechanics. Whenever you have a chance, the man was amazing. Him and another guy who I should have mentioned earlier, Eddington. Eddington wrote a philosophy of the physical sciences book. And he has this thing about we're searching for, he's on the epistemology of science and how we search for things and how we do it. He went a little bit wild at the end. He went to things that they didn't like, but those two people are just worth reading no matter what. Okay, Paul Dirac understood this loosening of axioms about 95 years ago when he wrote the following. Okay, and it's worth to go through it. I want to read it. The steady progress of physics requires for its theoretical formulation a mathematics which gets continually more advanced. This is only natural and to be expected. What, however, was not expected by the scientific works of the last century was the particular form that the line of advancement of mathematics would take. Namely, okay, everyone realized that the math had to get more complicated. Math has always been getting more complicated. But he says it went a different way. It went a special way. Would take, namely, it was expected that mathematics would get more and more complicated, but would rest on a permanent basis of axioms and definitions. while actually the modern physical development have required a mathematics that continually shifts its foundation and gets more abstract. What does he mean by more abstract? Non-Euclidean geometry and non-commutative algebra, which were at one time were considered to be purely fictions of the minds. This is a physicist talking about mathematicians, they hate each other. Okay? Purely fictions of the mind and pastimes of logical thinkers have now been found to be very necessary for the description of general facts of the physical world. So two of those examples we used. Okay, it seems likely that this process of increasing abstraction, by me, increasing abstraction means less and less axioms, less and less structure. Okay, it seems likely that this process of increasing abstraction will continue in the future, and the advance in physics is to be associated with continual modification and generalization of the axioms at the base of mathematics, rather than with a logical development of any one mathematical scheme on a fixed foundation. Okay, what he's saying is we have to use a lot of different mathematics in order to describe physics. And we have to use weaker mathematics with less axioms, less structure. By the way, when you have less axioms, you have less theorems. That's why actonians are not well known, because it's hard to prove a theorem about actonians. John Baez has a great paper on actonians. He has every single theorem about actonians, which is not a lot, okay? Because there's not a lot of axioms. That's the point of it. Okay, as physics progresses and we become more aware of more and more physical phenomena, larger and larger classes of mathematical structures are needed to get them by looking by fewer and fewer axioms. There is no doubt that if Dirac lived now, he would talk about the rise of actonians and even Sidonians. But I have something else he would talk about, namely, he would talk about category theory. So the Neural category theory, unifying concepts in mathematics, physics, and computing. Okay, so category theory is about this, weakening of axioms. Not saying what you're talking about. Category theory is derided as general abstract nonsense. We love that title, okay? Because it is, we like that. Okay, anyway, so you would need this. In order to describe more phenomenon, we will need larger and larger classes of mathematical structures and hence fewer and fewer axioms. What is the logical conclusion to this trend? How far can this go? Okay, answers the next slide. But I just want your thoughts. What's going on here? We're trying to encompass more and more phenomena. We're getting less and less axioms. What's the conclusion? Okay, physics wants to describe more and more phenomena in our universe. Let us say that we're interested in describing all phenomena in our universe. That is, we don't want to bracket out or idealize any phenomena. So she didn't like that bracketing out. What type of mathematics would we need? How many axioms would be needed for the mathematical structure to describe all phenomena, including Kripke coming in and stopping the balls rolling down from the thing? Okay, of course it's hard to predict, but it's even harder not to speculate. One possible conclusion, and this is where you get your induction stuff. One possible conclusion would be that if we look at the universe in totality and not bracket any subset of phenomena, the mathematics we would need would have no axioms at all. That is, the universe is totally devoid of structure and needs no axioms to describe it. This would finally eliminate all metaphysics when dealing with the laws of nature and mathematical structure. It is only the way that we look at the universe that gives us the illusion of structure. We see structure because we're bracketing out. I drove up here, I was looking at the clouds. I did not see structure. Okay, but you wouldn't let me come here and talk for 2 hours about the structure of the clouds, about the pretty clouds I saw coming up here. You wouldn't be interested in that. Okay, so you're only interested in regularities. Okay, total lawlessness. Again, this is speculation. I don't have anything to say about it, whatever. I wanted to call this talk lawlessness, but I didn't think he would let me use that in a physics.
Wheeler has a paper, Law Without Law.
Who?
Wheeler, John Wheeler. Law Without Law.
Right. So his thing is, right. So John Wheeler's thing is that also he calls it the participatory universe, that somehow human beings are in for collapsing wave functions, and the human being that was created to collapse the wave function does them. We're all in a superposition until we collapse the wave. I don't know that. I whatever. I mean, I like it and I wrote about it, but I don't think human beings collapse the wave. I used to think that, but I don't. Go, please.
Is it really total lawlessness, or would it just be total equivalence? Like if there is no axioms, you could also not differentiate anymore. And so in that sense, there would be not even chaos, it would just be total sameness, right?
I'm trying to bring you to nirvana. I'm trying to get you to see the world the proper way without bracketing out anything. I don't know. Okay, that question is beyond my pay scale. Is it beyond my pay scale? I don't have to. No, I don't know. This is speculation. I see there is structure in the universe, right? Okay. Now I'll drop my keys and show you again. It falls there, right? But my point is, I don't know what my point is. My point is, if we're trying to encapsulate all this, we're not going to have structure.
I think one interpretation of what she's saying may be that if there is no structure which is in a kind of bracketed way, then this is just a kind of monist substrate. It also has no structure, but how exactly would one view a total monist oneness perspective as a lawlessness?
I told you I'm trying to bring you to nirvana. That's exactly it. The universe is one, whatever.
So why is that lawlessness?
I thought you'd be angry at me for not bringing in the rule yet.
Not my rule.
Third rail.
This is very much related to the rule yet. I think that's it's a very interesting discussion with that. It's so let's act like the rule yet. Let's say it's not total lawlessness. There's every single possible things going on. And we humans are searching for some of those laws and idealizing. But saying that every law is in action is very similar to saying no laws. The main point here, the main point of this entire talk is that human beings are doing the finding. Go.
Yes, so on the rule yet, would you, I'm not quite sure about your language here, but would you say that the fact that you have states or cells and that they can evolve are two different things, or do you just, because well, we look at all the possible evolutions of all the possible cells, right? Would you just say we have a monist, just collection of states? And then would that monist, they are just cells, so to say, be one axiom, and so it wouldn't yet be at that total lawlessness that you add?
I have an answer to your question, but we have to move on. That's a way of evading the question. Go, please.
So I guess I see what you mean by, as we get more and more theories, we seem to be deleting things that we once assumed, right? So we think that the world works commutatively, all of our math is commutative, and then we find that actually we falsified this. There's better math that is not commutative. And it also,
don't use the word better, but yeah, there's other math that's not.
the better explains what we see. And the same is true with Euclid's axiom. But it also seems that these theories add quite a bit of structure, that just saying that we've like removed something from our previous assumptions is kind of like as a tautology, right? If we changed it, then we definitely removed something. But in fact, quantum mechanics is like an extraordinarily specific theory, right? That I would say is seemingly like, more specific than, let's say, our previous versions of particle physics. And that doesn't seem like it's pulling away axioms and making less axioms. It seems like it's much more specific and much easier to calculate.
In certain ways, it is much more specific, and in certain ways, it's not. So, it's expressed with real numbers, with the complex numbers, not real numbers, and complex numbers has less structure than real numbers. It's expressed with
complex numbers have more structure than real numbers.
For example.
well, they have all of the structure of real numbers in them, right? And then some, like, it's not
Yeah.
it's not that
You can say it the other way. You can say real numbers have all the structures of complex numbers.
you don't.
What's missing?
So I think you're gonna point to very specific things that we care about from real numbers, right? But those are just like, kind of to your point, right? Those are the things that we're looking for inside of real numbers that we care about, but we change what we care, what the things that we're looking for inside these number systems. And so I can, say as a matter of just mathematics, that because the reals are a subset of the complex, the complex numbers in fact contain all of the structure that the reals do, and then some.
Okay, okay, so given any polynomial in complex numbers, they can be, there's a factor. So it's a closed field.
I think maybe you have a different, you're disagreeing on what you mean by structure.
Maybe.
Right?
Yeah.
Or strength. Let's move on.
Yeah, sure.
Category theory.
Category 50. Anyways, this talk should have been called lawlessness, not even talking, just lawlessness. I have a T-shirt that says lawlessness with the explanation, but no one understood what the hell I was talking about.
In New York, you read that?
Well, in New York City,
In
everybody
New
wears
York.
T-shirts that says I love NY, which stands for I love Yanofsky. And whenever I see people who say, "What is that?" I'm gonna go over to them and say, thank you very much, I love you too, but. Let me get the right- Okay, third paper, why does mathematics work so well? Okay, a major question in the philosophy of science involves the unreasonable effectiveness of mathematics and physics. Why should mathematics created or discovered with nothing empirical in mind so perfectly suited to describe the laws of physical universe? To answer this, we review a well-known fact that the defining properties of the laws of physics are their symmetries. Okay, so let's recap. You ready? We find physical phenomena. We use mathematics to discuss it, and math grows, as physics grows, math has to grow. Now we're talking the following question. Why is math work so well? Why is it that every single physics paper has to have the math in it to describe it? Okay. By examining the symmetries of physics and mathematics, we show that the effectiveness is actually quite reasonable. In essence, we show that the regularities of physics are a subset of the regularities of mathematics. Okay, one of the most interesting problems. Okay, so this is the unreasonable effectiveness of mathematics. Let me just give you the background of the title. Mr. Wigner, who we mentioned before, Professor Wigner, that we mentioned before, in 1960 wrote a paper called "The Unreasonable Effectiveness of Mathematics in the Physical Sciences." And it's in a very interesting paper. I don't think anybody's ever read it. Okay, but the question makes up for itself. I know nobody's read it because when I read it, I was like, wow, that's pretty amazing. Just a sidebar, there are certain things that no one's ever read. Okay, so let me just give you two examples. One is for physicists, if you take quantum mechanics, there's a thing about whether or not there's hidden variables. And everyone says, oh, there are no hidden variables. After all, von Neumann proved in 1932 that there are no hidden variables. And there's a book of von Neumann, and he proves that there are no hidden variables in 1932, 1933. Okay, comes along Mr. Bell in 1965, and he says, or 1962, I've read that book paper, and the proof doesn't really work, which means for 30 years, everyone quoted that paper, but no one actually ever read it. Okay, that's not a criticism of physicists. I'll tell you a criticism of computer scientists also. You ready? Everyone knows that Alan Turing proved the halting problem is unsolvable, right? You know what the halting problem is? I gotta check the survey to see if you know the halting problem. You know what the halting problem is? That you can't tell a computer whether it halts or not? Turing never proved it. It's not proven, it's not in the paper. Go look in the paper. But literally from 1930 till about 2000, 70 years, everyone assumed that he proved the unsolvability of the halting problem. He proved the unsolvability of another problem, but everyone just thinks it's a halting problem. The halting problem wasn't shown to be unsolvable till the 1950s. So nobody reads papers.
Nothing's changed.
Nothing's changed. Okay, next, that was 2 minutes to waste time. Why should mathematics so perfectly describe the workings of the universe? Okay. Significant areas of mathematics are formed without. Did I do it? I want hearings of people I agree with. Significant areas of mathematics were formed without anything physical in mind, and yet such mathematics can be used to describe the world. How are we to understand this? Okay. Okay, so here's some examples of the unreasonable effectiveness of mathematics. We mentioned some before. Einstein needed non-Euclidean geometry. Heisenberg invents matrix multiplication, which existed beforehand. Okay, one of the more famous examples is the predictive ability of mathematics is the 1846 discovery of Neptune by Urbain Le Verrier, simply by making some calculations about the abnormalities of the orbit of Venus. Okay, so Uranus was going around, but every once in a while Uranus would have strange anomaly, and somebody pointed this out to this guy, and he told the astronomers, using calculus, he figured out, and he said, if you look here and here, exactly in this place, you will see that there'll be a thing called Neptune. There'll be a planet there, and they called it Neptune. It's just an amazing thing. Other examples are Dirac. We are going to read Dirac, right? I told you. Predictions of the existence of positrons. Maxwell did something else. These are all examples of using math to find physical phenomenon. But this is even more. Even more amazing is that there existed entire established fields of mathematics long before physicists realized that they were useful for understanding various aspects of the physical universe. Conic sections, studied by Apollonius in ancient Greece, were used by Kepler in the beginning of the 17th century. This is like 2,000 years later, to understand the orbits of the planets. Complex numbers were invented in the 1500s in Italy, okay? And then 500 years later, 400 years later, they're used to describe waves, and they're used to describe quantum mechanics. It's amazing. Non-Euclidean geometry was developed decades before it was used in an essentially way for general relativity. Details of these and other remarkable discoveries can be found next. Okay. Okay. Why should mathematics be so good at describing the world? Of all thoughts, ideas, and ways of expressing things, why should mathematics work so well? What about other modes of thought? Why does poetry fail to describe the exact movements of celestial bodies? Why can't music capture the full complexity of a periodic table? Why is meditation not very helpful in predicting the outcomes of experiments in quantum mechanics? The problem of why mathematics works so well was famously addressed by the Nobel Prize winning physicist Eugene Wigner in a paper titled The Unreasonable Effectiveness, spelling mistake, of Mathematics and the Natural Science. Wigner did not arrive at any definite answer to his question. He wrote, quote, "The enormous usefulness of mathematics in the natural science is something bordering on the mysterious, and there is no rational explanation for it." Albert Einstein described the mystery succinctly. How can it be that mathematics, being, after all, a product of human thought, which is independent of experience, is so admirably appropriate to the objects of reality? Is human reason then without experience merely by taking thought able to fathom the properties of real things? He doesn't come up with an answer either. Okay, but we're going to talk about some other people's answers. To be clear, the problem really arises when one considers both physics and mathematics to be perfectly formed, objective, and independent of human observers. With such a conception, one can ask, why these two independent disciplines harmonize so well? So some people invented mathematics, some people found physics. Why are they getting along so perfectly? So that's the question. Okay, many researchers have pondered this mysteries and offered various solutions to the problem. Theologians and Platonists and realists solve the problems in their own way. The reason most cited to answer the unreasonable effectiveness is that we learn mathematics by examining the physical world. So okay, so I explained. We understand some of the properties of addition and multiplication by counting stones and sheep. We learn geometry. This is a true story. Seriously. I was driving with my father. I must have been 5 years old. I was driving my father in the country, and there was a field full of cows. And I asked my father how many cows there were. And he said to me, very simple, add up how many legs there are and then divide it by 4. It's a true story. I remember just thinking about that's really interesting. It's funny. It's funny, but it's true. So we understand by counting stones and sheep. We learn geometry by looking at physical shape. The main problem with the solution, so this is a seeming good solution. We say as follows, that the world is a physical thing. We learned mathematics in our world, and so we do it that way. Why is the hidden world of subatomic? The main problem with the solution is that mathematics is very useful in areas distant from human perceptions. Why is the hidden world of subatomic particles so perfectly described by a mathematics learned from observing macroatomic, larger things like stones and sheep? Why is special relativity, which deals with objects that move near the speed of light, described by mathematics that was learned by watching objects that move at normal speeds? So these are some of the problems with this answer, that human beings learn mathematics from the physical world. I'm not saying it's wrong, I'm just saying this is something. Okay, while these and other purported solutions to the unreasonable effectiveness of mathematics have some merit, the mystery still remains. Deficiency in most of the discussion is that it's assumed that everyone already knows what mathematics is. Okay, so we're wondering why mathematics is described, why physics is described by mathematics, and everyone knows what mathematics is, but I'd like to give you a definition of mathematics. The true nature of mathematics is usually taken as so obvious it's not even discussed. In our discussion, we take aim to rectify this by giving an exact definition of mathematics. So I wrote a paper with Mark Seltzer about the nature of mathematics and symmetry, and this is what we want to push here. Okay, so before we start talking about a definition of mathematics, I have to give you a definition of physics. What is physics? As physicists, you should know that. To say what a physical law describes some physical phenomenon is a bit naive. It is much more. As a first attempt, we might say that each law describes many different physical phenomena. For example, the law of gravity describes what happens when I drop my spoon. It describes what happens when I drop my spoon yesterday. So this is symmetry of time. It describes what happens if I drop my spoon on the planet Saturn next month. Okay, the law of gravity should describe that. The law of physics describes a whole bundle, keyword bundle, of many different phenomena. However, this definition is not enough. A single physical phenomenon can be perceived. We're not describing what's happening. Nobody describes physics as what's happening. We're describing what we perceive happening. Okay? A single physical phenomenon can be perceived in many different ways. Physics states that no matter how a single phenomenon is perceived, it should be described by a single physical law. For example, we talked about the law of gravity a minute ago. I want to now talk about it again. The law of gravity describes my observation of a spoon falling in a speeding car while I am in the car. So I can be driving the car and I have a spoon and I drop the spoon and I want to do it. I want physics to tell me how long it took for that thing to fall. A stationary friend's observation of the spoon falling in the speeding car. I'm driving my car, I see the spoon falling. You're not driving your car, you see a spoon falling. The laws better be the same of describing when that spoon is going to hit the bottom of the car. An observation by someone standing on his head near a black hole of the falling spoon in the speeding car on Saturn. All these have to be described by one physical law if we're going to describe gravity. Every physical law describes a large bundle of perceived physical phenomena. A single law should be able to describe all the diverse perceived physical phenomena. Oops. The question then arises is how to classify all the perceived physical phenomenon into different laws. When do two perceived physical phenomena really represent the same physical law? Physicists use the notion of symmetry. Scientists have extended this definition of symmetry to describe physical laws. Okay. So we're gonna get a little bit into symmetry here. For example, physical laws are symmetric with respect to location. Whether I do an experiment in Pisa or Princeton, it should be the same. Symmetric with respect to time, today and tomorrow. So symmetric with respect to orientation, whether the experiment is oriented this way or this way. Okay, we should get back the same result. Okay, there are many other types of symmetries that physical law have to obey. Galilean symmetry, relativity, demands that the laws of motion remain unchanged if a phenomenon is observed while stationary or moving in uniform constant velocity. Special relativity means it's going to be the same if you're moving close to the speed of light. General relativity says it's the same if you're moving in an accelerating framework, et cetera, et cetera. Local symmetries, global symmetries, continuous symmetries, discrete symmetries. There's a hell of a lot of things going on here. There's a guy who's dead, his name is Victor Stenger. He wrote a book and he calls it all point of view invariance. Everything has to be, the laws of physics have to be invariant with respect to your point of view. Okay. The real importance of symmetry came with Einstein. This is Einstein's greatest revolution, greatest work ever. Okay, and I'm just saying that because I can. Einstein formulated the laws of special relativity. Prior to him, one first found a law of nature and then found its symmetries. In contrast, Einstein used the symmetries to discover the laws. Let me explain to you. He said, you know what? I want laws of nature to be the same, whether I'm standing still, whether I'm going constant, or whether I'm going at the speed of light. I want them all to be the same. Now he took that and he said, okay, now let's find a formula that describes that. That's an amazing thing. So he didn't find, so this is what you were talking about before. Do you find it in tandem? Do you find it in the math first or whatever? That's what he was doing. He first said, this is what I want. I want to be able to be going at close to the speed of light, and I want to know what that law is going to be. Okay, what the law is going to be. Okay, in order to find the laws of special relativity, he posited that the laws must be the same for a stationary observer and an observer moving close to the speed of light. Given this presupposition, he went on to formulate the equations that describe special relativity. This was revolution. Okay. Einstein had realized that symmetries are the defining characteristic laws of physics. Before Einstein, physicists would say a physical law. You give me a physical law, it satisfies symmetries. After Einstein, they say whatever satisfies symmetries is a physical law. That's another way of saying the same thing, predictable physical phenomena. Whatever satisfies symmetries, that's what we're studying. Otherwise, we don't study. We bracket it out. Okay. To elaborate, Einstein's revolution was a realization that a physicist selects from the many different perceived physical phenomena those that have symmetry. Those perceived physical phenomena that exhibit symmetries are bundled together and called the law of physics. Okay, great. Symmetry is very important. This is for Emmy Noether's law, very, very fundamental about that. Don't have time for it. What is physics? This is a broad definition of physical laws. Since the laws are applied in every, fine, this is very important. With this broad definition of physical law, it is not hard to see why the laws have a feeling of being objective, timeless, and independent of human observation. Okay, so when you walked in here, you thought, oh, the laws of physics are out there, I'm gonna find them, and that's what I want to do the rest of my life. Okay, and I'm showing you why you have that feeling. Since the laws are applied in every place at every time and from every perspective, they have a feeling of being out there, objective, physically out there. However, we can look at it another way. Rather than saying that we are looking at many different instances of an external physical law, we may say that we humans select those perceived physical phenomena that have some type of regularity and bundle them together to form a single physical law. We act like sieves. I'm saying this over and over and over again. You're going to get nirvana just by hearing me say this thing over and over and over. We bundle together what is the same physical law and we ignore all the rest. We cannot eliminate the human element in understanding the laws of physics. Nirvana, okay? When you realize that it's not really out there. We described it, we made it, we created it by selecting those things that have the symmetry. Okay, great. one more type of physics. This is my own words, me and my friend Mark Seltzer. Before we proceed, we must mention a symmetry that's so obvious it has not been articulated. Okay, I have never seen anyone say it. The law of physics must satisfy symmetry of applicability. What the hell is that? That is, if a law works for a particular physical object of a certain type, then it will work for any other physical object of the same type. Okay, for example, if a law is true for one positively charged subatomic particle moving close to the speed of light, then it will work for another positively charged subatomic particle that's also moving close to the speed of light. You can change the things. Now, obviously, you have to be careful about which law you're changing the things for. You have to be very specific about what physical element you're talking about. So I dropped my keys, and if you dropped a pen, you would have the same thing. In contrast, that law might not work for a macroscopic object moving at a slow speed. The perceived physical phenomenon for all these objects will be bundled together as one law. Symmetry of applicability will be of fundamental importance when we discuss the relationships of physics and mathematics. So this is a new symmetry, but again, it's so obvious that no one ever said it before. Great. Let's talk about mathematics. Sorry, go.
So one question about the symmetry of applicability. What stops us from just saying, like, so one thing we'd like to say is like positively charged particle moving close to the speed of light has this behavior. This other one has the same behavior. If they had different behaviors, what's to stop us from saying, oh, this one has a different type because it's defined by its behavior versus this other one?
Right.
Like,
So when you're making your law, you have to specify all the different properties that your particles or your objects that you're dealing with have. And if you find an anomaly, that means you didn't state your law properly. For example, Newton showed me how long it would take for the keys to fall to the floor. Then comes the 1900s and they find subatomic particles. And you know what? Subatomic particles doesn't follow Newton's law. So we have to change that. So beforehand, Newton never said, this works for all macroscopic particles. He just said, take an object, take another object, whatever. Then we got smarter and smarter and we said, you know what? Newton's law works exactly for such and such elements, and we had to be very specific. So as we get more and more advanced, we can specify the subset of objects for which these things work.
right, but my point is then what we'd like to say is like independent of the observation of that behavior. We know it's this type, therefore it will have this behavior. But if we're looking around at stuff in the universe, we observe the behavior and then infer the type from that. So I'm saying like, it seems less useful if you have to observe the behavior to determine if it fits into this type versus being able to say this is of the type, therefore it has the behavior. Do you understand the difference I'm pointing out?
No.
Okay, so like,
I got 15 minutes. I didn't define mathematics in. We'll talk about it after class. Okay, you ready? I'm gonna go through some of these. Long ago, a farmer realized that if you take 9 apples and combine them with 4 apples, so great, you now know what physics is. Let's talk about what mathematics is. Okay. Long ago, a farmer realized that if you take 9 apples and combine them with 4 apples, there will be 13 apples. Not long after that, it was noticed that if you take 9 oranges, not apples, and combine with 4 oranges, there will be 13 oranges. That is, if you swap every apple for an orange, the amount of fruit remains the same. At some point, an early mathematician looked at many instances of this and bundled, keyword bundled them all together and summarized them with this pithy method thing. 9 plus 4 is equal to 13. This pithy little statement encapsulates all the instances of the type of combination. The expression will be true for any whole discrete objects that can be exchanged for apples. By the way, it's not really true. Okay, let me give you a nice example. Ready? When my kid was young, my wife sent me out to buy Pampers, okay? And so I went and I bought Pampers and I said, what size? And she says, size 4. They didn't have size 4, so I bought 2 size 2. 2 plus 2 is equal to 4, okay? It didn't work. Okay, so you have to be careful when you go shopping. Okay, does the rule not work? Okay, here's another example. You ready? Take 2 piles of sand and add them to each other. Okay, what do you get?
A heap.
You get one pile of sand. A pile of sand on top of another pile of sand is a pile, so 1 + 1 is equal to 1. Okay, so you have to classify what you're talking about when you talk about things. You're not talking about pamper size. I know that mistake, and I won't make that mistake again, ever. Okay, and you're not talking about piles of sand. But when you're talking about discrete objects, you can exchange those discrete objects of what you're talking about. Let's talk about topologists. They just talk about something called the Jordan curve theory. Okay, this says that any closed, that means starts and finishes at the same point, a non-self-intersecting curve on a plane splits the plane into an interior and exterior. So, okay, anyways, if you make a big squiggly on a piece of paper that doesn't turn, and then you close it, no, it's not necessary. It's not necessary. It's not necessary. And then you close it for where it starts, but then no matter what, on the plane, there'll be an interior part of the thing and there'll be an exterior. Right? So that's a major theorem in topology. Whatever, anyways, but it's an interesting theorem. Main point, if you have one curve and then you change it for another curve, you're going to get also an interior and exterior for this one and for that one. Okay? I'm not saying anything strange here, just like if you do it for apples, you could do it for oranges, you could do it for this curve, you could do it for that curve. It's an amazing thing. Somebody once asked me, when I was in graduate school, they asked me what I study in graduate school. So I told them this theorem and they were like, weren't impressed. And so he said, tell me something else that you learned when you're in graduate school. And this is a guy who had absolutely no background in mathematics whatsoever. And so I told him about the pigeonhole principle. And you know what the pigeonhole principle? It basically says if you have n + 1 pigeons going to n pigeonholes, one of the pigeonholes will have more than one pigeon. And so I wanted to find something that anybody can do. And he says to me, you go to graduate school to learn about that? What? That's the simplest thing in the world. What? Really? Whatever. Anyways, so, okay. There's something called the Hilbert-Stellensatz. It's something in algebraic geometry. It's about radicals and ideals and something like that. Main point, if you change a radical for another radical, you get a different ideal, something like that. In topology, you have something called the Hurewicz map. It goes from homotopy to homology. Doesn't matter what these things are. Main point is, if it works for a topological space X, then it works for a topological space Y. If it works for the K dimension, then it works for the K prime dimension. Main point, you can change what you're talking about and you still get the same theorem. It has a feel of symmetry of applicability. Okay, let's go on. Okay, in these examples, we focus on changing the semantics of the mathematics. We exchange oranges for apples. We switch one closed curve for another closed curve, et cetera, et cetera. We swap one ideal for another ideal. We claim that the ability to alter the semantics of mathematical statements is the defining property of mathematics. So just like we define physics as those things that satisfy symmetry, we're going to define mathematics as those things that satisfy this changing of values. Okay. So that is a statement is mathematics if we can swap what it refers to and it remains true. Okay, so associated with every mathematical statement is a class of entities called the domain of discourse. That's from logic. They call it a domain of discourse for that statement. The statement is stating something about all the elements of this domain of discourse. When a mathematician says for any integer n, he's describing the domain of discourse for what he's talking about. Or he's going to say, take a Hausdorff space. He's describing the domain of discourse. When a mathematician says for any, let's see, be a co-commutative, co-associative, co-algebra with an involution, whatever the hell that means. So he's describing, he or she is describing that domain of discourse. She is setting up the domain of discourse for that statement. If the statement is true for some element in the domain of discourse, it is true for any other. Notice that the associated domain of discourse for a single statement consists of many types of entities. This is exactly what physicists do too, also have to do. They have to define the domain of discourse in what their phenomenon is talking about. Okay, so if you have some phenomenon, you have to say what type of thing it is. And symmetry, you change those two elements in it, you will still have, it will stay in the same. It will stay, the truth of it will stay the same. So that's true in physics, it's true in mathematics. Okay, this swapping of one element in the domain of discourse for another can be seen as a type of symmetry. Okay, so, okay, I have to bring in logicians here. So this is called, I call this symmetry of semantics. What are you talking about? Semantics, what are you talking about? Okay, and again, if you swap one element, if you change the location of an experiment, you get the same result. If you swap one element of the domain of discourse in a mathematical statement for another element, you get the law. Okay, so with using this symmetry as a definition of what mathematics is all about, we can do exactly what we did, what Einstein did. Mathematicians would say mathematical statements satisfy symmetry of semantics. But now me and my co-author are saying, but they would say any statement that satisfies symmetry of semantics is mathematics. It has to satisfy it. Okay, so that's our definition. Okay, logicians call this valid. Statement is valid if it's true for any member of the domain of discourse. What I'm trying to do is, so I'm not changing that. What I'm trying to do is I'm saying this validity, making something valid. What's valid? Something is true if it's valid, if it's true for every element of its domain of discourse. Well, if it's true for every element of its domain of discourse, I want to call that a type of symmetry. And I want to say mathematics is true for only valid statements, no counterexamples. But the point is, I'm looking at it the same way physicists. The novelty we are expressing here is that validity can be seen as a form of symmetry, and that this symmetry is the defining feature of mathematics. Okay, this is nice. Mathematics statements have other types of symmetry too. For example, we want to talk about the number 6. We can call the symmetry of syntax, not symmetry of semantics, the way you express things. You can express things in many different ways. 6 is equal to 2 times 3, or 2 plus 3 plus 2, or 59 divided by 6. Similarly, you could talk about a non-self-intersecting continuous loop, a simple closed curve, or a Jordan curve. Doesn't matter what you call it. Okay. Other types of symmetries mathematical statements possess are so obvious and taken for granted that even mentioning them seems strange. For example, mathematical truths are invariant with respect to time and space. If they are true now, they will be true tomorrow, and they were true before human beings existed. If they are true in Albany, they are true in Alpha Centauri. It is similarly immaterial if the mathematical truth is asserted by Mother Teresa, she's a good person, or by Oswald Teichmuller, he was a Nazi who did amazing mathematics, but he was a student who got killed fighting for the wrong side. Anyways, he was a horrible beast of human being, but whatever statements he made were true. Okay? No one cares where, when, or in what language of a theorem is stated. It's even irrelevant if the mathematical statement was stated at all. It didn't have to be stated. It's still true. Nobody could have stated it. It's still true. So all these are different definitions of what mathematics is. Okay. With mathematics satisfying all these different types of symmetry, it is easy to see why mathematics, like physics, also has this feeling of being objective, timeless, and independent of human observer. Okay, so we said about this for physics. We find physics, but then we say, no, it's objective, it's out there, it's not us. Okay, but it's not really objective. I mean, we found it. Okay, so too mathematics. If we use this definition of mathematics, since the facts of mathematics apply to many different objects, are discovered by many different individuals working independently, and in many different times and places, one can start believing that math is somehow out there. But we need not make that leap. Symmetry of semantics is at the core of how we determine mathematical truths. Human beings function like a sieve that picks out and chooses amongst the thoughts. Okay. We found order within the randomness of the human mind. So math is all in the head. There's lots of different strange thoughts in your head. We found some of them ordered, and we call those mathematics. Okay. Okay, great. Why mathematics works well at describing physics. 5 more slides and we'll let you go. Okay, and the idea is as follows, is we have a bundle of physical phenomena. We call that physics, perceived physical phenomena. We have a bundle of mathematical statements. We can bundle them the same way. Okay, so let's read this. Armed with this understanding of why nature of the nature of physics and mathematics, we can tackle the question of why mathematics works so well at expressing physical laws. Let us look at 3 physical laws. Our first example is gravity. A description of a single instance of a perceived physical phenomenon of gravity might look like this. On the 2nd floor of 5775 Main Street in Brooklyn, by the way, there is no Main Street in Brooklyn, I looked it up. New York, at 9:17 with 54 seconds, I saw an 8.46 ounce spoon fall and hit the floor 1.38 seconds later. I made that. Okay, while it might be totally accurate, it's not very useful and it's not a description of all the instances laws of gravity. As we explained, a law consists of all the perceived instances of that law. The only way to capture all the bundled perceptions of physical phenomena of a particular law is to write it in a mathematical language which has all its instances bundled with it. Only Newton's formula of F equals G times M1 times M2 divided by D squared can capture the entire bundle of perceived physical phenomena of gravity. Okay? By substituting the mass of one body into M1 and the mass of the other body into M2, the distance into D, we are describing an instance of gravity. So again, physics has all this bundle of possible things. Math has all a bundle of possible things. We say what M's are, we say what D's are. These are real numbers corresponding to masses and distances, okay? And only then could we bundle them together, and only mathematics is able to see that. In a similar vein, okay, so we have the Euler-Lagrange theorem. Doesn't matter. We don't have to go through the examples. By symmetry of some syntax, we can even write the formulas in the Esperanto. It is irrelevant how and in what language the mathematics is expressed, as long as it is mathematics, because only mathematics can capture the action principle in all its instances. Okay. Okay. In terms of symmetry, you are saying that the physical symmetry of applicability is a special type of the mathematical symmetry of semantics. That's what we're saying. So we're bundling things together. We're bundling perceived physical phenomenon. We're bundling what we mean by certain mathematical statements. And the way to see it is one bundle is a sub-bundle of the other. Okay, and this explains why it's so useful. Mathematics is so why mathematics is so useful for symmetry. Because we made a definition of what physics is. We make a definition of mathematics or what mathematics is, and they work out perfectly. If there is a mathematical statement that can describe this physical law, then we can substitute different values with different objects of these applied. In terms of bundles, we are saying that every bundle of a perceived physical phenomenon is a sub-bundle of instances of mathematical law that describes it. Okay, you know what? I'm just going to read the big words. The point we are making is that mathematics works so well at describing laws of physics because they are both formed in the same way. Okay. Okay, on the deepest level, one could ask why there are any regularities at all in perceived physical phenomena. Okay, why is it that the universe has any regularities whatsoever? Okay? Why is it that when I do an experiment here and I do an experiment in New York, I get out the same results? Okay, and the only way to answer that really is the anthropic principle. Namely, I couldn't have asked the question if it wasn't true. Okay, you need a human being or intelligent life. We're not living in a Salvador Dali painting because anybody living in a Salvador Dali painting couldn't come up with the rules. Okay. Okay, question. What about math? Why is there such good math thoughts? So I explained why there's good physics. Why is there such good math thoughts? We have 2 more slides and we'll finish up. Perhaps we can, well, anyways, you know what, you'll read it, you'll watch it on the video. Okay, while we have not eliminated all the mysteries, we have shown any existing structure in our perceived physical phenomena is naturally expressed in blank. Thank you. Okay, I have copies of the papers that I have. Including the library in Babel. You're welcome, and if you come tomorrow, it'll be very nice.
We could take more questions if you.
I'm not going anywhere. I just want to shut this off because if I say I don't know something, I don't want anyone.
And people on Zoom, if you want to ask questions, now would be the time.
Seems to me like what you mentioned before, the pigeonhole principle might be at work here because the universe, whether mathematical or physical, is so huge and our mind is so limited. So in order to comprehend either universe, maybe we are forced to see some patterns.
Right. So all of science is compression. We're compressing all the phenomena that we see, but we're not going to lossy compression, not lossless compression. We have to compress things. And we have to lose information because we can encompass the entire universe. Okay, and that's what physicists are doing. They write books, they're compressing a lot of phenomenon in those.
Thank you.
I have a question. It's a really great talk, by the way. I find it very interesting, so thank you. I'm not a mathematician and I'm not a philosopher, so maybe it's just all over my head. I'm an applied scientist, and I'm struggling to see the falsifiability of some of these statements. Like, if we go back to the lawlessness one, it's like, I think the gist of what you're saying is, in the limit of infinite generalizations, you can describe everything, the whole universe. The more you generalize, the more you can describe. How would you falsify that? I mean, you can't take the limit of infinite generalization.
Right, so that's total speculation.
Right, okay.
Okay, then I can't, I'm just saying,
Okay.
it seems like it goes that way. However, falsification comes in very well with this whole thing. Okay, namely, if you find some phenomenon that does not bundle well.
Sure, right, okay.
Then you have it.
So you
Another
could
thing-
disprove it,
Right.
right,
So.
by example,
Right.
counterexample. But so the same with the statements later about anything that is a symmetry is a physical law. Like, are there not an infinite number of symmetries? And so how could you falsify that? Except by proof by counterexample.
Right, and we come up with new symmetries all the time. Right, and we come up with new symmetries and we come up with, and we make up symmetries and by the way, certain physical phenomena don't satisfy certain symmetries. CPT or something like that, the charge particles.
CP violation.
Right.
Yeah.
Charge parity time.
So we have to find, we use the symmetries, we use the violation of certain symmetry, chirality. Chirality. We use that to find. But you're right, that thing with taking the end and whatever, that's total speculation, that's a violation.
Okay.
Sure. Somebody had their hand up. It's been a pleasure.
Any more on Zoom? In that case, let me ask one last thing. What exactly is the lawlessness in mathematics? In physics, at least you described it with some examples, like saying here are phenomena for which there are laws, and there may be others for which we may just have to either idealize or it may be hopeless. In mathematics, everything is about structure in some way or another. So what exactly is lawless mathematics?
Right. So two stories. First of all, category theory. I don't know what lawlessness is, but I think it'll be well expressed in category theory because it has so many possibilities of what it could be. But also in mathematics, so we have the notion of a group. You all know what a group is, right? Okay. Now let's say you leave out the inverse. Okay. So then you have the structure is called a monoid. Okay. And then you could leave out the fact that it's associative. And so then it's called a semigroup or something like that. And then you go on, and then you can leave out associativity, you leave out the unit, and then they actually have a name for this thing. It's a set with a multiplication. That's all it has. okay, and it's called a magma. Magma as in, stuff that comes out of the earth without any structure, any form whatsoever. But like you said, I can't express, this is really nirvana, I can't express the structurelessness of things, the lawlessness, without having a structure. So I can say, look, here's a structure that has just a set and a multiplication, that's it. But again, I'm saying, we can talk about the category of those things. But again, I'm expressing it in a structure. I can't express the ineffable without saying it.
Any more questions?
In the beginning, probably in the presentation, you said that it's really hard to define randomness. And I just wanna hear your thought, what you think about my claim. And my claim is that it's really easy to define randomness, and randomness is precisely related to like cohomograph complexity.
Perfect. So, you've heard of cohomograph. Let me tell you what cohomograph complexity is. Take a string, okay? The cohomograph complexity of that string, whatever it is the size of the shortest program that you can find that would print that string. Okay? And the idea is as follows. Let's say I have a string that goes 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. So then I can just write that as a short computer program and saying print 0, 1, 2,000 times. That's a short program. Now, let's say I have a program that says print me the digits of pi. Well, the program to print the digits of pi are about that long. That's a little bit more complicated, but it's something I can do. Now, let's say that 35 by 35 random thing, okay? Let's say I wanted to write a program that does it. Well, let's just forget it for the fact that you have a built-in, every one of your computers have a built-in random number generator in it. The only way to possibly do that is to just say, here's all the numbers in that 35 by 35 table, and then print out all the numbers one after the other. And the point is, that doesn't seem to have any structure in it. And so the only way you can compress it to a small program is to print it out itself. In other words, input that whole thing as part of the program. Okay, so that's called the cohomograph complexity. So again, given a string, the cohomograph complexity is the size of the shortest program that prints that string. Okay, and the idea is the shorter the program is, the less complicated it is. 0, 1, 0, 1, 0, 1 is not very complicated. Digits of pi, not very complicated. What I showed you, very complicated. Great. Now, here's the theorem. Ready? Cohomograph complexity is you cannot write a program that calculates the cohomograph complexity of a string. In other words, if I give you a string and I say, okay, find me what's the size of the shortest program that gives me that string, I can't find it. It can't be written by a program. It's like the halting problem. Can't be done. Now, here's the idea. We can't know that there's no structure in it. We can't know that that thing that I produced doesn't have some deeper structure and it could all come out in some smaller program. We human beings are not good at, machines are not good at doing that. So just like you can't know whether or not a program with a certain input will halt, that's called the halting problem, so too you cannot know whether or not there is structure inside a string. It's an amazing fact. So listen to what I've been talking for 2 hours, telling you that we search for structure, we find it, and now I'm telling you, you can't really know whether or not your law is the best law possible. By the way, that's very much related to your Popper.
Popper falsifiability.
Right, you can't know. Popper says you can't know whether or not a rule is a law of physics is a real law of physics. It's an amazing fact. That means all of science is tentative.
So we can say that randomness is easy to define, but it's hard to approach.
Relevant, right. Let's use the word structure. Structure is easy to define. It's hard to tell if it can be found or not. Relevance kind of has a feeling of human beings have relevance or not. I'm sorry, human beings say this is important, this is not important. Okay, we're all physicists here, so we think everything mathematicians do is irrelevant. And the mathematicians think that whatever. Go.
It's is that kind of like our choice of like basis units? Because it's like the meter, it's like, all right, North Pole to the equator, divide by 1,000,000. Like that's pretty dang arbitrary. It's like, oh, the second, it's an earthly convenience. But when we combine them by their transformations via nature, we get the speed of light, which seems to be pretty important. Is it kind of along those lines that we can choose something arbitrary from our perception? And by focusing on nature, we can kind of, I'm not sure my question.
Me neither.
Okay, continue on.
I don't know which part.
It might be a sampling question. It's like once, whether or not that's the elementary thing may be irrelevant, but it's the relationship between those things that's important.
Can I say, you guys know what Vsauce is?
Yes.
The Vsauce has Michael Stevens, he has this great experiment thing he's describing. It's not his, but I've seen it in other places, but he does it beautifully in a thing called causes, one of his Vsauce things. He does as follows. It's the nail, you have a nail, you have a shadow, and you have a light. Okay, now, those three things are determined by each other. The height of the nail, if the nail was taller, the shadow would be taller. If the light was from a lower down point, it would be, the shadow would be further, okay? Now, he's not saying, what he says is that it's not that one causes the other, okay? The height of the nail and the length of the shadow and the height of the light, they don't cause each other, but there is an intimate relationship that can be determined by them. Okay, and that's what physics is all about, is to find that relation. We're not finding what's causing what. We're just saying this is the relationship between the light going down, the nail, and the shadow of the nail. Okay, in some sense, this is exactly, you have to look at Newton's law from this point of view. It's not one thing is causing the force. We're just describing what is some type of relationship between these elements. Force, the mass, the distance, they're all some type of relation. So even, what I'm trying to say is even a law is not a law. I said that like a New Yorker. Even a law is not a law. Sorry. It's just a relation with, what physics is trying to do is find a relationship between entities.
Hey, I have a question. I'm on Zoom here. I don't know if you guys can hear.
There you go.
James, say that.
Yes, can you hear me? Okay, great. Yeah, I just had a question about the relationship between symmetry and maybe how mathematics views equivalences. And I wanted to get your opinion on whether mathematics, what makes it so impressive is just that it's consistent. And that's maybe what makes it predictive and helpful. So it's just that idea of like logic itself is just consistent by definition, and building up those structures gives you mathematics and then physics.
So I have a 9-year-old daughter who's very upset by the fact that she's allowed to divide any number by any other number except one. Okay, not except zero, except one number, namely 0. And she wants to know why I can't divide by 0 also. And she's very upset by this. And I say, well, what should 5 divided by 0 be? And she doesn't know the answer. But the point is, her teacher told her she's not allowed to. Okay, and you don't tell a 9-year-old you're not allowed to. And you don't tell a 9-year-old, what type of socks to wear and how to set up her hair. So she's very upset with this. The point is, in some sense, the consistency comes out from the rules we set, okay? You're not allowed to divide by 0 because if you were allowed to divide by 0, then you have the following statement. 0 times 5 is equal to 0 times 7. It's a true statement. Okay, if you would divide by 0, then you'd have 5 is equal to 7. 0 times 5 is equal to 0 times 7. True. Divide by 0, cancels out the 2 zeros. You have 5 is equal to 7. And you won't be able to do mathematics very well if you start off with 5 is equal to 7. Okay, so the consistency comes out from the fact that if anything gave you an inconsistency, you would stop. Okay, let's get back to Euclid's rule. Okay, so I'm sorry, Euclid's story of the fifth postulate. It's a fascinating history. It goes as follows. Euclid had some 5 axioms of geometry. I'm talking 200, 300 BC or AD, whatever, Euclid, whenever Euclid. And all the axioms are very, very, very easy to describe, except the 5th axiom. Okay. And so what the 5th axiom is this long, complicated theorem. It says if you have a line and you have another point, there's exactly one line such that it's parallel. And that for years, and I mean centuries, they try to prove the other theorem, prove the 5th theorem from the other theorems. It didn't go. They tried and tried and tried, and they couldn't get it. And so this big, ugly theorem wasn't good. So then they decided to do the following. Okay, and this is the beginning of non-Euclidean geometry. Let's say the 5th axiom is false. Let's say for a given line and a point, there's 2 lines that you can draw that's parallel to it. Okay? Now, what they try to do is, when you proof by contradiction, try to get a contradiction in your mathematics from that. So you have the first 4 axiom, and then you have this warped 5th axiom, and you try to get it. And what they found was they couldn't find a contradiction. Okay, when you add the 4 normal axioms and you add this negated 5th axiom, they couldn't find the contradiction. It went on for years and years until they realized, hey, there's something called non-Euclidean geometry, which fits very well if you draw that one line on a ball and then you make a dot on the ball, then you can draw 2 other lines that are somewhat parallel. Okay, so the main point is we were looking for a contradiction. So when you define mathematics, when you do mathematics, if you come to a contradiction, buzz, you don't publish it, you don't tell anybody about it, you go back to another project. Okay, because we select out when we say, oh, this is going to be a contradiction, forget about it. So that also has that's also, so what I'm trying to say is mathematics can also have this selection process, and it's not just that it's consistent, it's we choose it to be somewhat consistent. By enforcing, by telling our little angels not to divide by 0, we are teaching them not to have contradictions in them. It's tyrannical, but it's okay, math is very tyrannical. Any other questions? Anyways, it's a pleasure. Thank you. You're all been tomorrow, yeah.